Hello everyone, I am Mitradip Bhattacharjee and today I am going to present disposable and flexible polymer sensor patch for α-Amylase detection in human blood serum. This is the outline of my presentation. So I will start with introduction, then we'll discuss the materials and methods section. Then I will discuss the results and discussion, followed by the conclusions. So to begin with, disposable and flexible sensors are indeed needed in biomedical and healthcare applications because of hygiene requirements. At the same time, they should provide an affordable solution for point-of-care testing and large-scale deployment. In this view, herein we report flexible polyimide-based disposable sensor patch for the detection of α-Amylase in blood serum. The concentration of α-Amylase in blood serum is a potential indicator of health issues such as pancreatitis and pancreatic cancer, and an affordable solution to detect its concentration could benefit many. Here, the detection is based on thermal Marangoni circulation inside a microfluidic droplet of starch FeSO4 salt solution, which detects the α-Amylase concentration upon addition of blood serum. It was observed that the temperature difference between the droplet substrate and the ambient sets in thermal Marangoni and natural convection inside the droplet. The performance of the microdroplet based sensor was best at temperature difference near about 18 to 20 degrees centigrade. The sensor is capable of detecting 20 to 110 units per liter concentration of α-Amylase with a maximum change of 80% of electrical resistance across the microdroplet when the substrate temperature was kept at around 40 degrees centigrade. And the sensitivity was found to be equal to 0.88% unit per liter inverse. The response of the sensor was also compared with pathological laboratory results, and both were found to be in agreement. The presented sensor has the potential to be used in point-of-care device for detecting of α-Amylase in real time. So let us see what are the materials used. So the materials used in this case was basically iron 2 sulfate heptahydrate, potato starch, and the enzyme, which is amylase, that has been extracted from porcine pancreas. Polyimide sheets were employed as a substrate of the sensor. So here, on the right side, you can see an image of the circuit associated with the sensor, which is made on a flexible substrate. Now, the electrode fabrication process is described over here. If you look at the process, a polyimide substrate was taken initially, and then metal was deposited using hard mask. The thickness of the metal was 50 nanometer. So initially a 10 nanometer gold layer was deposited, over which a 50 nanometer thick platinum was deposited, which acted as a electrode. So in this image, you can see the optical image of the flexible fabricated sensor. This is the sensor patch in the image A. Image B show the microscopic image of the electrodes. Image C and D shows the rotational speed with temperature difference and the effect of bending, respectively. The experiments were performed on the fabricated flexible polyimide sensor with a droplet of FeSO4 solution. The polyimide substrate was selected due to its suitable thermal conductivity and temperature sustainability. Apart from this, polyimide has a suitable surface energy for this application because we are working with droplet and micro droplet, so the contact angle was very important. So this polyimide substrate has suitable surface energy for this application. A series of experiments were conducted for different temperatures from 25 degrees centigrade to 75 degrees centigrade, and the rotation inside the droplet was recorded using a digital camera. a small graphite particle were introduced inside the droplet to record the motion. The rotational speed inside the droplet with temperature difference between the substrate and ambient is illustrated in figure 2C. And figure 2D shows the effect of bending. Higher the bending, the response was even higher. So in this image, you will find a schematic illustration of the experimental setup, which is shown in image A. Image B shows the response of the sensor with different concentration of α-Amylase. And image C shows the response of the sensor at 40 degrees centigrade, along with the response of the blood serum, that is biosamples, which is indicated in green spheres. The experimental setup described in figure A, and the 3 microliter α-Amylase was added into the starch salt mixture at t equal to 0 second. It was observed that the sensor performance was best at 40 degrees centigrade when the amylase activity remains highest. The range of the detection was 20 to 110 units per liter, and the sensitivity was found to be 0.88% units per liter inverse. This is the readout circuit. For this purpose, a constant voltage excitation circuit with offset compensation is required. Apart from this, amplifiers are also used. The enhanced accuracy was ensured by the design complexity of the circuit using 2 OPA177 precision operational amplifiers having very low offset voltage, which is around 25 microvolt, and drift, which is 0.3 microvolt per degree centigrade. The precision amplifiers are part of the sensor conditioning circuit. In order to power the mentioned dual supply plus minus 5 volt op-amps, a voltage inverter was also used. The simple relation between output voltage and the resistive sensor value can be given by the equation as shown in point B, where V bias was 0.5 volt for appropriate biasing of the sensor and to avoid any noise due to electrolysis. The bias applied was kept low purposefully to avoid any electrochemical interference. The value of R gain was kept 708 kilo ohm to maximize the output voltage range while keeping the values within the input common mode voltage. This is an optical image of the fabricated circuit, which is fabricated on a flexible substrate. In conclusion, the study shows that the rotational motion inside the droplet increases with the increasing temperature. Further, the bending of the substrate also increases the rotation inside the droplet. The droplet was made conductive by using FeSO4 salt, and then starch was added to make it specific towards amylase reaction. It was observed that the sensor could detect amylase from 20 to 110 units per liter concentration with a sensitivity of 0.88% units per liter inverse. Further, the best sensor performance was recorded at 40 to 45 degrees centigrade. In addition, a flexible PCB was developed as sensor readout system to measure the concentration of the amylase in blood serum. The sensor response was compared with biosamples, and both the results were found to be in agreement with each other. I would like to acknowledge our funding agencies. Thank you. These are the references used in this particular study. And finally, thank you for your attention.